When you put an object on the end of a spring and pull it back and release it, it will bounce up and down, repeating the same sort of motion over and over. This style of motion is known as simple harmonic oscillation, but for this video, we're just going to focus on how this applies to mass on a spring. The first scenario we'll look at is a vertical spring with a mass hanging on the end. The mass will start out at rest, but when we pull on it, it will start to bounce. What must be present in order for our spring to bounce up? The answer is restoring force. The restoring force is a force that acts in the opposite direction of the motion of the spring as the spring is trying to return to its equilibrium position, the position where it is at rest. Since we're talking about an ideal spring in this video, we can model this restoring force with the equation force equals negative k constant times position. Our k in this equation represents the spring constant of our ideal spring, which is the amount of force it takes to move the spring a distance. The standard metric for k is newtons per meters. We then multiply this spring constant k times our change in position x. This is important as according to this equation, the farther out we stretch our spring, the more force will be generated. Let's think about this in the context of the Newtonian equation, force equals mass times acceleration. If we set this equal to our new equation, force equals negative k constant times position, we can see that our acceleration will increase linearly with our displacement. Our mass and our spring constant will both remain constant, so the only values that will increase are the magnitude of our acceleration as we increase displacement. Now let's keep our displacement constant. However, we don't know what our mass is, and we can only measure acceleration. If our k equals 100 Newton meters, and we are displacing our spring 1/2 meter, and our resulting acceleration is 10 meters per second squared, what must the mass of our object be? If you answered 1/5 of a kilogram, you're correct.